Suppose we are checking the passenger manifest of a large cruise ship as it is being boarded. Before any passengers get on the ship, the 500 crew members are already in place, ready to give the passengers an exciting vacation on the open ocean. Once they start boarding, we find that 50 passengers board every minute until all 2,000 passengers are on board. We might want to know how many people are on board at any particular point in time, say m minutes after boarding begins. We have several ways to do that. We could say that the number of people on board is 500 crew plus 50 passengers for each minute that has passed since boarding began. We can express this as P, people on board, equals 500 plus 50 times m. So for any m that you give me, the number of people on board is calculated using the function rule 500 plus 50m. Another way we could find the number of people on board after n minutes is to add 50 to the number of people we knew were on board at a previous time 1 minute earlier. This is an example of a recursive rule. We get the current answer based on the previous answer. We can even use a recursive rule to predict the number of people who will be on board in the minute yet to come, which is time m plus 1. All we need to do is add 50 to our current count at m minutes to get the upcoming count at m plus 1 minutes. This is also a recursive rule, but now we are getting the next answer based on the current answer. The word recursive means that we are using a recurring or repeating process. We generate new values based on previous values. Here's a table comparing the three rules we just looked at. In the far left column, we have m, the number of minutes that have passed since boarding began. The next column contains the results of the function rule calculation. Notice that it only depends on the value of m that we choose, and we could skip around the table as much as we please to calculate the ship's population for any time m. For example, if I wanted to know the population at time m equals 6, I would only have to plug in 6 into this formula and calculate the answer of 800. Now we're using what's called subscript notation to keep track of which minute's population we are using. The capital P stands for population, and the small number below and to the right, which is called a subscript, tells us the minute that goes with that population. And we might use a formula to find the correct subscript for the minute m we are working with. P sub m plus 1 means to use the next minute, current minute m plus 1, to find the population. P sub m minus 1 means to use the previous minute, m minus 1, and P sub m means to use the current minute. Next, we have a recursive rule in this column that says that the ship's population at the current minute m is found as the population in the previous minute, m minus 1, plus 50. This calculation is very simple, but it does depend on knowing the count at time m minus 1. Look at the formulas in this column and compare with the function rule formulas in the previous column. They look different because they work different, but they give the same result, as you can see. The last column is also a recursive rule, but this one says that the population in the upcoming minute, m plus 1, will be the population in the current minute, P sub m, plus 50. We are essentially predicting a future population value based on what we know right now. We can use these rules to determine the ship's population at time m, or even when the population might reach some particular value. For example, how many people are on board at time m equals 30 minutes? Since m is a fairly large number, we might get lost while repeatedly calculating values one after another with a recursive rule. In cases where our variable is a large number, a function rule is often the best approach. We would simply plug in a value for m. So our function rule said that the population at time m is 500 plus 50 times m. Since we know we want the population at 30 minutes, we'll plug in 30 for m. That gives us 500 plus 1,500, or 2,000 people. Another thing we can determine is how long it will take until there are 600 people on board. Now, it's not difficult to think of the initial crew count of 500 and then adding 50 and adding 50 again to get 600 people in 2 minutes. This is an example of how we often use a recursive rule intuitively. A function rule works well here too. We must solve the equation 600 people is the original crew of 500 plus 50 times some number of minutes m. We can solve this for m by first subtracting 500 from both sides. That gives us 100 equals 50 times m. And then we'll divide both sides by 50 to get m equals 2. So no surprise, we got the same answer as we did with the recursive rule intuitively of 2 minutes. There are 600 people on board after m equals 2 minutes. So now let's see if we can plot this sequence of population numbers versus time on the Inspire calculator. We're going to start a new document and we're going to select a graph screen. Now, when you select the graph screen, you're going to get a blank screen like this. And what you want to do is to press Menu, 3 for Graph Entry Edit, 7 for Sequence, and 1 again for Sequence. You'll end up with this screen down here. Now, I've highlighted in yellow what needs to be changed to match our problem. The default is going to say U1 of n equals blank. Erase all of that and type in P of n equals P of n minus 1 plus 50. This is the recursive formula that we had in the center column in the table. The initial term here, 500, represents the initial quantity of people on board, which was the crew. And then we want to change our values of n to start at 0 and go all the way up to 40. If you plug in a value of 40 into m, you're going to see that that's going to give us the 2,000 people, passengers on board. Now when you do that, your graph screen is going to come up blank. And the reason is because these values, these scales on the axes, are not sufficient to display all of the data. So we're going to have to double click them to edit the axis scales. We want our y value to be 3,000 and we want our x value to be 50. If you double click these two numbers here and put these numbers in their place, you should get a graph that looks something like this. So here is the sequence that we entered in, and these are the individual sequence values from n equals 1 to n equals 40. You can see that this sequence of population values is a linear or line-like scatter plot. Each time that we move to the right by 1 minute, which means our run is equal to 1, the population rises by 50. So the slope, which is the rate of change, is 50 people for the rise divided by 1 minute for the run. Rise over run gives us the rate of change. We're changing by 50 people every minute.